In this video, we solve problem 13.6.026.mi from the Larson and Edwards Calculus Early Transcendental Functions text, 7th edition. We're asked to use the gradient to find the directional derivative of the function at the point P in the direction of PQ. So we have this function and we've got P and Q. And remember what the directional derivative is. That's just the slope in a certain direction. So the first thing that I would do is I would state the definition of the directional derivative, or the formula for the directional derivative, in terms of the gradient of the function. So if I want the directional derivative in the direction of a unit vector u hat of a function at x naught, y naught, what I need to do is I need to find the gradient of f at that point and then dot it with the unit vector in the direction that I'm going in. So we've got to find the unit vector in this case. We have P and we have Q. That will allow us to find the vector PQ. We can make it a unit vector by dividing by the magnitude. We also need to find the gradient and evaluate it at the point P because we want the directional derivative at P. So we evaluate this at 7, 3 in this case. And then we'll dot them. And that's going to give us the slope of the surface in the direction from P to Q at the location x equals 7, y equals 3. So that's the plan. To start, I would, well, we can do either one of these first. You can evaluate the gradient and plug in, or find the gradient and then plug in 7, 3, or you can find the unit vector. Either way is fine. And then once you find both of those vectors, we're going to dot them. So I'm going to find the gradient first. Remember, the gradient of f is a vector. If f is a function that depends on two variables, the gradient has two components. One is a partial derivative of f in the direction of the first variable, and the other one is the partial derivative of f in the direction of the second variable. And in this case, it's pretty easy to find those partial derivatives. The partial derivative of 3x squared with respect to x just comes from applying the power rule from calculus 1. We've got 3 times 2, which is 6, times x to the 1 last power. It's just going to be an x to the first. And then since there's no x here and there's no x here, that 4 minus y squared, that's a constant. The derivative of that constant with respect to x is 0. And of course, we're just treating y as a constant whenever we compute a partial derivative. Okay, now we're going to do the same thing, but we're going to compute the partial derivative with respect to y. Derivative of 3x squared with respect to y, if x is a constant, is 0. And then we're going to subtract the derivative of y squared. Well, you bring the 2 down, so you're going to have negative 1 times 2, so negative 2, times y to the 1 less power. 2 minus 1 is, of course, 1, and the derivative of 4 is 0. So that's our gradient in general. Let's evaluate that at the particular location that we're interested in. So we're substituting in x equals 7, y equals 3 to this vector here. So you're replacing x with 7 and y with 3. And so we get 42 and negative 6 as the components of our gradient function at the point P. And now we need the unit vector from P to Q. So we need to first find the vector PQ. Now remember how that works. You take the coordinates of Q, which in this case are 2 and 8, and you subtract the coordinates of that initial point, which in this case are 7 and 3. 2 minus 7 is negative 5, and 8 minus 3 is positive 5. Now that is not 1 unit long. If we want to make it a unit vector, we have to divide it by its magnitude. So we need to compute the magnitude of PQ now. So you take the components, you square them and add them and take the square root. So we're going to have 25 plus 25, or 50, or if you prefer, you could call that 25 times 2. So we're going to get 5 times the square root of 2. Maybe you already knew that because of trig. I hope that you saw that and you were like, it's going to be 5 times the square root of 2. If you didn't, that's okay. But think about it. There's a triangle. Go -5 units in the x direction, 5 units in the y direction. The hypotenuse should be the length of the side times square root of 2. Okay. So hopefully if we're making that reference back to trig, or just geometry, we recognize that the length of that side should be that. It's consistent with our intuition. Okay, so now we've got a vector, we have its length, or magnitude. In this case, it's the same thing. And then we want to use that to find the unit vector in the direction of PQ. So you just take PQ and you divide by its magnitude. So you've got a vector with components 5 and -5, and you're dividing each of those by 5 times the square root of 2. And then the 5's reduce. You end up with this. If you wanted, you could rationalize. You don't have to, though. Multiply by square root of 2 over square root of 2. If you do, you'll get negative square root of 2 over 2 and positive square root of 2 over 2. Hopefully you recognize those from trig. Recognize those. Might remind you of cosines and sines of angles that are related to that 45-degree angle in the first quadrant. Okay, so now we've got u hat. Now the directional derivative is a number, it's a slope. It's a slope of the surface in a particular direction. So now that we have the two vectors, we're going to take their dot product, and the dot product of those two vectors is going to give us the directional derivative. Now remember what the dot product is, or one way that you can think of the dot product. The dot product of a unit vector with another vector is giving you the length of the projection of that vector, or it's actually the assigned length of that projection of that vector onto the unit vector. So it's like we're looking at sort of the shadow of this onto the unit vector, and looking, or in other words, looking for the component of this that is parallel to the unit vector. It turns out that the magnitude of that component is going to be the slope of the surface, or the absolute value of the slope of the surface in that direction. And the sign really just depends on whether the slope is going up or going down. So that's one way that you can think about that if you want to. You don't have to, but you can if you want to. Now we've got 42 times the negative square root of 2 over 2 plus -6 times positive square root of 2 over 2. And so, of course, 2 goes into 42 21 times, 2 goes into 6 3 times. So I've got -21 of these minus 3 of those. So it looks like we have -24 square roots of 2. And that is our slope. Okay, so that's it. That's how we find the directional derivative and what it means. Let me know if you have any questions.